Welcome to our heat transfer class, where we are going to delve into the use of numerical methods to solve heat conduction problems within solids. This video was made with the support of InnoEnergy. The topic of the application of numerical methods to the heat conduction in solids is divided in several lessons. There is at least one video for each lesson. The introduction is divided into several parts. Let's move back to the diffusion equation for conduction heat transfer. The heat diffusion equation is an energy balance per unit of volume inside a solid. We can evaluate the energy stored per unit time, the energy per unit time generated inside the control volume, and the inputs and outputs by conduction through the walls of the control volume. Now, we apply the Fourier's law to evaluate conduction fluxes. Making the necessary arrangements, the diffusion equation is found in 3 dimensions and transient regime. The temperature distribution is in scalar field, with a given value at each point in the space. In the transient regime without phase change, the solution gives values of temperatures at each point change over time. The temperature distribution can be found by solving the diffusion equation with specific boundary conditions. After knowing the temperature field, we can calculate the heat flux at any point in the solid by applying Fourier's law. The heat diffusion equation may also be expressed in cylindrical coordinates, also in spherical coordinates.
The problem with this equation is its complexity. There are different approaches to obtain the temperature field and, eventually, its evolution over time.
Analytical solutions. The hypothesis of one-dimensional steady-state conduction greatly simplifies the heat diffusion equation. For Cartesian coordinates and constant thermal conductivity, the diffusion equation is a second-order differential equation. For solids without internal heat generation, this is the Laplace equation. For cylindrical coordinates, the simplification of the heat conduction equation can also be solved analytically. The same for spherical coordinates.
Usually the analytical solution, if it can be found, of an ordinary or partial differential equation can be expressed in terms of known mathematical functions that can be calculated as accurately as we wish for any values of their arguments. The solution of the mathematical model will predict the real behavior of a physical system as long as these hypotheses are fulfilled. The solid must be homogeneous and isotropic. The thermal conductivity does not depend on temperature. The volumetric heat generation, if any, is uniform. The boundary conditions are such that the heat conduction can be considered one-dimensional. The geometry of the solid is simple. That is, flat, cylindrical or spherical walls. The solution of the mathematical model will predict the real behavior of a physical system as long as these hypotheses are fulfilled.
Application of numerical methods.
For solving multidimensional cases with non-symmetrical boundary conditions, real solids, and the evolution of temperatures over time, analytical solutions cannot be found. We can look for numerical methods to solve numerically differential equations. Although the different numerical methods have a common base, there are some differences. These differences make them better suited for solving different types of problems. In heat transfer, the finite difference method is used, although not exclusively. We will describe this method later in the video about solving the transient regime. The application and solution of the heat diffusion equation implies assuming a continuous model of matter. However, there is a third way, which does not solve the diffusion equation. The energy balance method is based on dividing the medium into a sufficient number of volume elements, domains, or nodal regions, and then applying the energy conservation equation to each element. This division is known as meshing. In this way, a system of equations is obtained, one for each element. As will become evident, this approach enables to analyze many different phenomena such as problems involving multiple materials, embedded heat sources, or exposed surfaces that do not align with an axis of the coordinate system.
Summary of advantages and drawbacks.
If it can be found, an analytical solution of an ordinary or partial differential equation can be expressed in terms of known mathematical functions that can be calculated as accurately as we wish. For numerical methods, approximating derivatives by differences is intrinsically associated with an approximation error. Increased accuracy requires much more data storage as well as increased computational time. However, analytical solutions can be found only for ideal solids, for simple geometries, and for simple boundary conditions. But you don't have to worry. Using numerical methods you can solve multidimensional cases with non-symmetrical boundary conditions, real solids, and the evolution of temperatures over time.
Please watch the video that explains the energy balance method.